I'm sorry to interrupt. You said you put it in the chat.
Yes.
I don't see anything.
It should be a PDF document that is called Workday.
I don't see it either.
All right. We're gonna figure it out.
I see it. I was able to download it.
Where how did you pull it up? It may be are
Well,
you
it
on a
was just in the
laptop or are
chat.
you on a phone?
I'm on a laptop, and it was just in the chat, and it allowed me to download it.
Yeah, that may be why. If you're on a phone, you may not be able to see it. But at any rate, I'll make sure you get it. I'll share my screen and then you can screenshot it. Either way. So yeah, back to the question. What two factors uh if you have a reaction happening on a molecule with a pre-existing stereo center, what two factors
How
affect the
close it
outcome?
is,
Okay,
how
great.
close it is, and
Yeah.
then
So the
how
proximity,
bulky or large it is.
yes, the size of it and the proximity of it to the reactive site. Thank you. Was that you, Joy?
Yes, sir, it was.
Yeah. Thank you. So size and proximity are my two factors that dictate like how much influence that pre-existing stereo center is going to have on my reaction. Come on, iPad. Let me share this and we're going to jump back on this example the next example that we were looking at. All right. So when we look right here on this example, right, the reactive site is here. Right, that's my reactive site. The stereo center, the pre-existing stereo center is next door to it, right? So the closer that stereo center is to the reactive site, the more impact it's going to have on the outcome of the product distribution, right? Because you're going to get an unequal mixture of stereoisomers. Do you move it further away, then it's going to change the outcome. Sometimes it's drastic how much the outcome changes. So let's look at the next example. And let's see if we can figure this out. All right, let's read the question first. Always read the question, look for what it's asking you. And then after that, you can start, let the wheel start turning about how to solve it. But it says oxymercuration of the same compound produces two products in relatively 50-50 ratio. It says draw the products, number one. Number two, explain why there's a decrease in the ratio. So does anybody remember that reaction from part one? That's gonna save us about 20 minutes right there.
Is it like the oxymercuration?
Hmm. Yeah. What type of reaction is that? Anybody? Who do I owe lunch? Amaria?
Yes,
Yes, you
sir.
owe Mark.
I ain't forget now. Put your cash app in the chat. It's better to get
Okay.
lunch on Friday than Wednesday anyway.
You're right. Thank
Yeah.
you.
Free lunch Friday. All right. So what is oxymercuration? Let's take a couple of minutes and refresh ourselves on that, and that's gonna help us to answer this question. First of all, let's go back to the top example. What type of reaction is hydroboration? If you look at that top example. This YouTube video is going to be silence. All you're going to hear is static.
Is this reaction like an electrophilic addition?
A little bit, yes, but it's not quite the same outcome. The double bond is acting as a nucleophile in this case.
You add the H to the most, substitute it in the OH to the least.
Who was that?
Is Kayla.
You're 100% correct. It's a way to convert alkenes into
The
alcohol.
alcohol.
Is that right?
Yes.
And what other what's the term that we use for what you just said? The technical term. You said add the OH to the least substituted carbon and H to
Anti-Mark Markovnikov.
anti-Markovnikov. Very good. Let me write that in here. If I can fit it. I'm abbreviated. Anti-Markovnikov. So what other reaction was in that same class? We learned both of these reactions at the same time, right? Oxymercuration is also a way to convert alkenes into alcohols. But what's the difference? And what do we call that difference?
You'll
And-
add the OH to the most substituted and the H to the least substituted. So you'll do that with Markovnikov action.
It's Markovnikov addition. Good, man, you own it. You earn that A. It's Markovnikov addition. Right, of H and OH. That's what we're doing. Basically, both of these reactions, in essence, are like adding water to an alkene. You add H to one side, you add OH to the other side. All right. So you said it's Markovnikov addition. What's the term for that? When we have an alkene and one side or the other can react in a certain way, what do we call that? What do we call that term? Anybody remember? Where you have a different region of the alkene that can react.
I forgot.
Is it the site? Oh, chemistry. I was thinking.
Oh, there you go.
Regiochemistry, right? That's the difference. That's the difference in, let me fix this. This looks terrible. Right, that's the difference in these two reactions. They have different regiochemistry. One, a different carbon in the alkene reacts based on the conditions. Why's my stylus acting up? Come on, you little dollar store stylus. Never mind, I'll just use my finger. All right, different regiochemistry. You should go back and look at that term because that's important for this reaction. So who can tell me what the product of this reaction is? Working knowledge of part one. I can't stress that enough. I have a working knowledge of part one. Who can tell me what the product is? I just gave you the pieces to it right here.
There would be an alcohol.
Okay.
At the end.
And where's the OH? Which carbon would the OH be on?
The carbon where the double bond is.
One of them, right?
Right.
Okay, which one? You're right. I'm just gonna pull you on down the path.
Is it the one to the left
The one
of
to
the
the
double?
right here, because you only got two choices.
Yeah, the one to the left, I think.
Okay, and we just said it's Markovnikov addition, right?
So it's most substituted.
So
So
the OH is going to the most substituted carbon. So it's going to be the carbon on the right.
Right.
Are
Yeah.
y'all following it?
Yes.
All right. Let me abbreviate this because I don't feel like drawing this whole thing. I'm old. Yes. I'll just put, let me just not do that. Let me just draw this like it is. All right, hold up 1 second. I'm just going to abbreviate the methyl groups too. And so on the double bond, the alcohol is going to end up over here. And I'm just going to draw it on the first one on the wedge like that. And then this is cut off. I didn't draw the rest of it. But we're okay with that. So that's one of my products. What would the other one look like?
it'd be the exact same except the OH would be
On the
wait,
wedge?
no, I'm sorry. The chiral center would be what?
Mm-hmm. This one doesn't change, right?
Right.
That doesn't change, but oh gosh, hold up. Let me zoom in on that. I gotta get some room. Guess that's one of the drawbacks of not having a real whiteboard. So my OH would be here. Is that right?
Yes.
So I have the one alcohol where they're both on the same side, and then one where they're on opposite sides. Let me fix this. That's not a radical. All right. What's the difference? Look, let's go back and read the question. The question says that and I promise I'm gonna slap this iPad. I promise I'm gonna slap it. Right. So what's the difference? Between this reaction and the one above it. Look at the question. It says that the ratio went down to 50-50 from 80-20. What changed?
Dr. Russell, can you scroll up a little bit?
Is that good?
I think the difference would just be how the silicone and the carbon, how it's blocking from one side is a steric interference.
So the steric interference is a given, right? Because you got a stereo center present prior to the reaction even happening. So that's going to cause steric interference regardless. But the question is, look at the regiochemistry. That's what I'm trying to get you to see. Look at the location of the OH in the first problem. Where is it in relation to the stereo center that's already present? How close is it? That's the question. Right, do you see up here? I'm gonna erase some of this highlighted stuff and zoom in. This thing is really dragging. Come on, bro. Do you see right here? Sorry about that. How the OH is like right next door to that chiral center. Can y'all see that? It's like one carbon away.
Yes.
And then if we go down here, what's the difference? Is it the same distance or is it further away now? In the top example, it was right here, wasn't it? The OH was on this carbon.
So it's further.
Is it not on the stereo center now?
When you say not on, what do you mean by that?
Like at first it wasn't. Never mind. I don't think. Never mind.
Let's go back and look at the double bond. You see where the double bond is, right? Is there something on my screen, like some water or something? Jeez. Right, do you see where the double bond is, right here? It's only those two carbons that's going to participate in this reaction. So it's going to be one or the other. But when we look at the product, we can see where the OH went, right? It went to, let me erase that. It went on this carbon, didn't it?
So the OH moved to the carbon with the double bond?
There's two carbons in a double bond, though. That's what I'm trying to get you to see.
I
But
have
one
a question, Dr. Russell. I'm
one of
sorry.
them, hold on one second. One of those carbons is further away from that reactive site than the other one. That's what I'm trying to get at. Go ahead.
So, when the double bond goes away,
Mhm.
like you can't have a stereo center with a double bond, right?
No.
So when it goes away, it creates one stereo center, but the other carbon is not one because it has two hydrogens on it.
Yes.
So it would be attached to the stereo center, meaning it would go closer, right? I don't know if I'm
Well,
making sense.
actually, it's actually
Okay.
further away.
Okay.
Where the new chiral center is being formed. You're right. The carbon right here can't be a chiral center, right? Because it's got two hydrogens on it. Right. But the one next door, the one I have highlighted in green, is a chiral center. And if you notice, that chiral center is further away from the reactive site, which I'm gonna highlight in a different color. I'll highlight it in teal, whatever it is, right? But if you look up here, that's not the case. It's actually closer. That's my pre-existing stereo center, and then that's my reactive site. You see the difference?
Yeah. So when we're determining what's closer, we're looking at the reactive site, not the OH group.
Yes, yeah, because the
okay,
OH is the
sorry.
product, but where it ends up in the product, that's what we mean by what the double bond is the reactive site, right? That's where the reaction takes place. So when we look at the double bond and then we look at the product, we can see, okay, this carbon right here in the double bond is the one that reacted, and that's where my OH ended up. So it's closer to that chiral center when you compare it to the reaction down here, where it was this carbon where the OH ended up, and then this is my chiral center. What's going on my screen? Right, you following? So it's further away. That's why the ratio went down. We opened up saying the two factors that affect the outcome the most are the size and the proximity or the distance from the reactive site. So in this case, the reactive site is further away. And so the fact that it's further away means that it's not going to have as much influence over that reaction. Let me write that down. Right? So if the reactive site is further away from that pre-existing chiral center, then the ratio is going to drop because the influence is going to be less. All right. And questions about that? Because y'all real quiet right now.
I have a question.
Mm-hmm.
So how do you know which one is the 80% and the 20%?
Well, up top we had them labeled, but there's another way too, right? The reason why A is 80%, and can you see that top reaction where I have A and B labeled?
Yes.
The reason why A is 80% is because of how the OH is oriented relative to the pre-existing chiral center. It's on the opposite side of it, so it's more stable that way.
Okay.
Right, so that's what we're looking for.
Okay.
You see how the B and B, both groups on the same side?
Yeah, I see what you're saying because one has a wedge and then
Right.
the staircase, and then the other one has both staircases. So
Yeah. You said a staircase? I never heard that before, but I like it.
well, the dash lines.
Yeah, it's okay. If that helps you to remember it, that's fine with me. It makes sense to me. All right, let's look at the third question. Hopefully this will click by the time you get to lunch. Go ahead. All right. Let's look at the third question. It says if the reaction and number 2, which is what we just did, is carried out with this substrate, when you change the methyl groups to tert-butyl groups, which are much bigger. All right, let me write that. Let me go ahead and put that in to let you be thinking about it. So the silicon will actually look like this. You have these 3 tert-butyl groups attached to it. Right? And that's bonded to oxygen. So if you change the methyl groups on silicon to tert-butyl groups, what do you think is going to happen to the ratio of the 2 isomers? Because we said that this was almost 50-50. What do you think is going to happen if I bulk up that group on the that's already there, this group right here? Right. What happens if I make that bigger? What do you think?
I think the ratio would go down a lot.
Would it go down? You mean, explain what you mean by go down. Make sure I understand what you're saying.
Wouldn't it be blocked like the 2 Burton? Don't they block the reactivity from it being so reactive?
Well, it wouldn't make it more reactive or less reactive, but it would play a role in making that ratio more unequal, right?
Okay.
You understand what I'm saying? So again, because it's all based on 2 things. It's either size or proximity.
Okay.
So the distance doesn't change, but if the size changes, then you're gonna also see, excuse me, you're gonna also see a change in the ratio. Make sense?
Yes, thank you.
All right. All right, let me put that in here. Sit down somewhere. Right, so there'll be an increase in the difference between the 2, the major and the minor products. All right, let me do this. How many of you were able to find that document in the chat? I can put it on my screen too, for those who need to screenshot it if you couldn't find it. Let me zoom out of that some. All right, so the document looks like this. The title is Workday, Stereochemistry Workday. All right, so how many of you have this? Were able to download it?
I have it.
I have it.
All right, do I need to put it up again?
Yes, can you put it up again, please?
No. Oh, my bad. Yeah, that I answered before I thought about remember what I was doing. I forgot I was teaching. All right, yeah, I'm just messing. Let me see right here. So I just uploaded it again.
Thank you.
Do you see it?
Yes.
Mm-hmm. So what I'm gonna do is I'm gonna make some breakout rooms. We got 39 people logged in. So I put 7 people in the room. I'll do 6. and it's it's going to be automatic assign. So I'm not going to assign. I'll just So it says you've been invited to join. So I want you to go into that breakout room. We're going to take about 10 minutes. I want you to work through number one, let me see. The first two examples on number two. And then of course number three. And then we're gonna work number four together. Because four is just like what we just did. All right, so I want you to do number one, the first two examples on number two, and then number three. We good? Got it? All right. I'm about to put it in the chat too. It's too quiet. Why y'all not working together and talking through these examples?
She had just asked a question.
Can you-
Okay, 1 second.
And I have it. I think I have it set so you can share if you want to share your screen.
I don't know how to do that. So I'm gonna just show what we got. So we had number 2. We only got to number 2 in 2 questions.
Okay.
For the first one, for the first Chiral center, we got the configuration was R.
Okay.
And we got that because looking at this center right here, we see that bromine is first priority.
Uh-huh.
And then the carboxylic acid is second.
Okay.
The third priority atom is this carbon down here.
Yep.
And then the fourth one is the hydrogen. And because it's on a wedge, it's reverse because it'd normally be
Yes.
counterclockwise, which is S, yes.
Okay,
And then
great.
for the second one, we got R because first priority is where am I? Okay, yes. Right here. This carbon right here.
Okay.
Because it's attached to the bromine.
No.
And the
first
no?
priority should be OH because you're comparing carbon and oxygen.
Oh, yes, yes. Okay. That's wrong.
That's okay though. I'm glad you gave your reasoning, which makes sense. But you're really only looking at the atom, the carbon and the oxygen. So okay, we're good with that. If you switch that around, what would it be?
So then 1, 2, 3. So it'd be S.
Okay. Wait a minute. You giving. Let me go over just a tad. Right. So iodine. So yeah, iodine, oxygen, and carbon. Iodine is bigger than both of those. Atomic number wise and atomic. So that should be 1. Oxygen should be 2. And then the
Yeah,
carbon.
that's what we had.
Okay. All right.
1, 2. Okay, yes.
Yeah. And then
So
that's going to
then-
change that.
Right.
So instead of it being R,
it's going to be S.
it should be S. No. H is vertical. H is vertical. So
Yeah.
Oh, yes. My bad. Yes.
Yep. All right.
So it will be R?
Yes, because H is on the
Yeah, that's
vertical.
what I thought, because H is on the vertical. You only change it if H is on the horizontal.
Horizontal, right. Did anybody get number 2? The second example, because I asked y'all to do the first 2. Did anybody get the second example on number 2? Any group?
I got it, but I don't know if I'm right.
Come on. Confidence. Have confidence in your abilities.
I guess I'll.
Can you share it?
I can't share my screen. I guess I can just talk you through it, what I have.
Okay. So first of all, how many chiral centers are there?
I think it's 3.
Okay, I agree.
So for the first chiral center,
Are you doing
on
the
the
one
far-
with chlorine?
huh? What did you say?
You're doing the chlorine one
No, the one on the far left.
with the aldehyde attached. Okay.
So I labeled the priority for the atoms or whatever, and I got the configuration BS.
Okay. This one, right? So this carbon was 1. This one was 2, and that one was 3. Is that what you did?
Yeah, no, I didn't do it like that. So
Is this carbon, carbon, carbon? So now you got to go to the next atom. So this is carbon, oxygen. This one here will be carbon, carbon. Even though it's a C double bond O, it's still a carbon. Right. So the point of difference is the oxygen. That's why that group on that side will be 1, that will be 2, and that will be 3. So, and then remember you got a hydrogen on a wedge. So that would be clockwise if I count it how it is, but because hydrogen is on the wedge, right, we'll call it R. I'm sorry, S.
Wait, can you explain to me how that's number one again?
So each group is carbon. Here,
Mm-hmm.
here. I'm sorry, not that. Yeah, here. Let me delete that. So each group that's attached is a carbon, carbon, and then a carbon.
Right.
Hold up, I think I screwed that up. All right. So yeah, so this one is attached to oxygen, and so is this one. But
Yeah.
yeah, so this should be one because
Yeah, that's
this
what
is
I thought.
yeah, this is bonded to oxygen twice, and then this one is bonded to oxygen once.
Thank you.
Thank you for catching that. So then that will be 1, 2, and 3. It's
So would it be
counterclockwise.
R?
Yes, because it's counterclockwise, but H is on the wedge. So we'll reverse it and call it R. All right. Go ahead, Brittany. What'd you get for the second one?
Um, so I did the first one wrong, so I don't think the other two are right. So I don't think I
Well, I
said
got S for the next two.
All right. Let's see if we can do them real quick. Sorry. I know we're out of time. This is going to be 1. And then you got carbon, 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 chlorine. So this is 2. And then this is 3. So 1, 2, 3. That's R. But the H is on a wedge. So we'll call that one S. And then the second one, the H is already back. So all we got to do is prioritize. So chlorine is going to be 1. That's 3. This side is going to be 2. And that is R for the final one.
Oh, is it R?
So this is
Oh,
1.
yeah.
And then over here, you have a carbon and a carbon. But this carbon is bonded to oxygen. So that makes it 2. And that makes that 3.
Yeah, but that's counter. No, it's clockwise.
Yeah.
So R.
Yeah.
Okay.
That's what it says.
Yeah, thanks. I was just clarifying my own mistake.
Okay.
Dr.
Thank you.
Russell,
Uh-huh.
so for the second stereo center, the one by the OH, you put the 2 by the chlorine
On
and the
this one?
3 on the other side.
Yeah.
So
So oxygen is 1. And then these are both carbons. One of them is bonded to chlorine. One of them is bonded to another carbon.
okay.
Even though that carbon is double bonded to oxygen, it doesn't matter. I stop at the carbon because that's my point of difference.
Okay.
All right, so that makes this side 2, and then that makes that side 3.
Dr. Russell, you said on the first one, the one with the CH3 at the end and the double bond to the O, that you switch it because the H is on
a wedge. Because remember,
so
the rule is to get H away from you to determine the configuration, right? So you want it pointed away from you. So if it's pointed towards you, then the configuration is going to be the opposite of what you see. Did that answer your question?
Yes, thank you.
All right. Well, I know we got to stop because we're 2 minutes over, and I know y'all got other classes. What I'm going to do is create a link, and I'm going to upload this to Blackboard too. I'm going to fill in the answers and upload it to Blackboard. And then what I'll do is I'll create a link in Blackboard that you can upload yours to for a bonus assignment for today for your participation.
Dr. Russell, can I email it to you because my Blackboard is down?
Okay. Yeah, you can do that.
Okay, thank you.
What were the number of problems that we were supposed to have done?
Look at that. Look at that. Just look at that.
I'm just trying to make sure I got the right stuff.
I gave you the right stuff. Let me take. Hold up. Number 1. The first 2 problems on number 2, and then number 3. And we were supposed to do 4 together, but we ran out of time.
Okay, thank you.
Mm-hmm. All right. Any other questions? Let me stop this recording too while I'm at it. I don't want people to hear